Hello, this is Yashveen. Today I'm going to be solving paper 4 variant 3 May June 2019 0625 physics. Starting with question number 1, figure 1.1 shows a distance time graph for a cyclist traveling between points P and V on a straight road. A. Describe the motion between Q and R. So Q and R shows constant speed. R and S. R and S shows deceleration. And S and T shows object at rest or a stationary object. B. Calculate the speed between U and V. Alright, so U and V, since this is not, we're not supposed to be calculating speed at a point but between 2 points, I'm going to be taking out the gradient between these 2 points, which is equal to y2 minus y1 over x2 minus x1. So the value of y2 is V, that is 600, minus y1 and the value of u, which is 440, divided by x2, that is the value of the coordinates of v, and that is 400, minus x1, the coordinate of u, the x coordinate of u, and that is 300. And this gives us the answer as 1.6 meters per second. Alright, C. After point V, the straight road continues down a steep hill. The cyclist travels down the steep hill. He does not apply the brakes and all resistive forces can be ignored. On figure 1.1, sketch a possible motion for the cyclist after V. Okay. Since this cyclist is cycling down a hill, he is going to be accelerating because as the height decreases, gravitational potential energy also decreases. But since that is the opposite of kinetic energy, his kinetic energy is going to be increasing and so does his acceleration. So I'm going to be drawing a graph which represents increasing acceleration, and that is going to be a curve upwards like so. Question number 2. Figure 2.1 is the top view of a small ship of mass 1.2 into 10 to the power of 6 kilograms. The ship is moving sideways at 0.04 meters per second as it comes into dock. The ship hits the bottom pillars with which move towards the dock wall. A. Calculate the energy of the ship before it hits the pillars. Alright, so we have the formula of energy as kinetic energy as half into mass into velocity squared, and that is equal to half into mass, which given in the question is 1.2 into 10 to the power of 6. I'm going to put the value of mass in brackets over here, and then we have the velocity, which is equal to 0.04 squared according to the formula, and so we have the answer of energy as B. The ship is in contact with pillars for 0.3 seconds as it comes to rest. Calculate the average force exerted on the side of the ship. Okay, so the formula of force is mass into acceleration, which is also equal to mv minus mu divided by t, or change in momentum divided by time taken. So since mu is basically mass into the initial velocity, that is the velocity, this velocity over here, but mv is 0, so I'm just going to be calculating with mu, and so we have the calculation as 1.2 into 10 to the power of 6 multiplied by the initial velocity, which is 0.04, divided by the time taken, which is 0.3 seconds. So this gives the answer as 4.8 into 10 to the power of 4 divided by 0.3, and this gives the answer as 1.6 into 10 to the power of 5 newtons. C. Assume that the kinetic energy calculated in A is used to do work moving the pillars. Calculate the distance moved by the pillars. Alright, so we have the formula of work done as force into distance. So the formula of distance is going to be work done divided by force. Work done is also equal to energy, and for that energy we're going to be using the kinetic energy value that we had in the question. So we have the working as work done divided by force is equal to distance. So work done is also equal to energy transferred, which in the previous parts is 960, divided by the force, the answer which we got in the last part. D. The dock walls sometimes have the pillars replaced with rubber tires. Explain how this reduces the possibility of damage when a boat docks. Alright, so we have the formula of force as mv minus mu by t, right? So is when the dock has rubber tires instead of the pillars, after the boat comes into contact with these tires, the time for contact is greater between tires and the boat compared to the contact time between tires and the pillars. So when the time in contact increases, the force decreases, and so the amount of damage possible also decreases. Moving on to question number 3, figure 3.1 shows a small submarine submerged below the surface of the sea. A. The density of the sea is 1030 kg per meter cube. Calculate the pressure due to the seawater on top of the submarine when it is 3 into 10 to the power of 3 meters below the surface. Alright, so we have the formula of pressure as density into gravity into height. Alright, so we have the answer of pressure as 3.1 into 10 to the power of 7 pascals. B. The submarine emits a pulse of sound to detect other objects in the sea. The speed of sound in seawater is 1500 meters per second. An echo is received with a time delay of 0.5 seconds after the original sound is emitted. 1. Calculate the distance between the submarine and the other object. So speed of sound is calculated by distance covered divided by the time taken. But since here in this question we are dealing with echo, the formula is going to be distance multiplied by 2 divided by the time taken, because not only do we have the sound traveling in one direction, it is going to go forward and then backward. So it's traveling twice the distance which it would normally do, because this is an echo. So we have this is the formula of speed over here, and shifting these time and 2 towards the left hand side gives us the formula of distance as speed into time divided by 2. So speed given in the question is 1500 multiplied by the time, which is 0.5 divided by 2, 2. Another pulse of sound is emitted through the air when the submarine is on the surface. An echo is received from a second object that is in the air. The echo is received 0.5 seconds after the pulse of the sound is emitted. Compare the distance of the second object from the submarine when the distance calculated in B1 with the distance calculated in B1. Tick one box, give a reason for your answer. Okay, since speed of sound is slower in air than speed of sound in liquid, that should mean if this sound is traveling at a slower speed, it would reach a smaller distance in the given area. Since speed and distance are directly proportional, speed of sound is slower in air, and that should mean in a given time, the distance traveled should also be slower. And so I'm going to be ticking the box over here, distance is smaller, and the reason is that speed of sound is slower in air. Question number 4. A. Water molecules escape to the atmosphere from water boiling in a pan. Water molecules evaporate from the surface of a bowl of cool water and also escape to the atmosphere. State two ways in which boiling is different from evaporation. Alright, so here we have boiling occurs throughout the liquid. And it occurs at a fixed temperature. B. Figure 4.1 shows a heater in a metal block. The power of the heater is 370 watts and it is switched on for 4 minutes. The metal block has a specific heat capacity of 420 joules per degree Celsius and a mass of 5 kg. Calculate the increase of temperature of the block. Assume all the thermal energy from the heat is transferred to the block. Alright, I'm going to be starting with converting 4 minutes into seconds since all of the rest of the values are given in standard units. So 4 minutes is equal to 4 into 60, which is equal to 240 seconds, the time taken. So we have the formula of specific heat capacity as energy divided by mass into change in temperature. Now we need to calculate the increase of temperature of the block, and that means the formula after shifting the rest of the variables is going to be energy divided by mass into specific heat capacity. Okay, and energy is not given in the question, but we are given with other values which are power and time. So energy is equal to power into time, which is equal to 370 into 240 divided by mass, which is 5 kilograms, and specific heat capacity, that is 420 joules. So we have the values as 88,800 divided by 2100, right? And then we get the answer as 42 degrees Celsius of change in temperature. Question number 5. Figure 5.1 shows a cross section of the inside of a vacuum flask containing a cold liquid. The walls of the vacuum flask are made of glass. So we have a stopper over here, silvered surface, vacuum, and glass. Alright, A. The vacuum flask is being used to keep a liquid cool on a hot day. Explain how the labeled features of the vacuum flask keep the liquid cool by reducing thermal energy transfer. Include the names of the processes involved. Okay, so this is going to be a long answer since we have 5 marks over here which need 5 points of answers. So we have silver surface first. Alright, silver surface vacuum. Next comes the stopper. B. Suggest a suitable material for the stopper. This can be anything, a wooden cork, or any suitable choice. Question number 6. A. Figure 6.1 shows wavefronts of a wave approaching a narrow gap and passing through the gap. The wavelength is unknown. 1. State the name of the process that occurs as the wave passes through the gap. This is diffraction. 2. A wavelength with half the wavelength approaches the same gap. On figure 6.2, draw 3 wavefronts for this wave as it approaches the gap and 3 more wavefronts as the wave continues behind it. Alright, so you see how diffraction occurs over here is the spreading of the waves would be larger if the gap between the barriers is smaller than the wavelength of wave. So if we have a wavelength half of this, the diffraction would be less. That is to assuming that the gap between the two barriers is same. So I'm going to draw some waves with a shorter wavelength which looks almost half of the wavelength, and its the diffraction is going to be less. B. Figure 6.1 shows 5 different types of electromagnetic waves. In the black column in table 6.1, write down the numbers 1 to 5 to show the order of wavelength. Write 1 for the wave with the shortest wavelength and 5 for the wave with the longest wavelength. Starting with the shortest wavelength, over here, that means the highest frequency. C1 state the speed of radio waves in air, which is equal to the speed of light in air, and that is equal to 3 into which is equal to speed of light in air, that is 3 into 10 to the power of 8 meters per second. 2. A radio station transmits radio waves with a frequency of 96 megahertz. Calculate the wavelength of these radio waves. So we have the formula of wavelength as speed divided by frequency. Speed in this question is 3 into 10 to the power of 10 divided by the frequency, which is 96 megahertz with 6 zeros, and this gives us the answer as 3.1 meters. Question number 7. Figure 7.1 shows light approaching a boundary between two terminals at speed v. The speed of the light after crossing the boundary is 1.3 v. 8. Determine the angle of incidence. The angle of incidence is the angle between the normal and the incident ray or the refracted ray. So over here we have the normal, which makes a 90-degree angle with both of the sides of the borders. So this total angle over here is supposed to be 90 degrees, and this angle between incident ray and normal is supposed to be angle of incidence. So if we subtract 50 from 90 degrees, we get the answer as 40 degrees, which is the angle of incidence.
Part B, calculate the angle of refraction. Okay, so normally the formula which is used is refractive index is equals to sine of incident angle divided by sine of refracted angle. But since in this question the light is moving from a highly dense material to less dense material, we will be using the formula Refractive index is equals to of sine r divided by sine I. And how do we know that the light wave is entering a shallower region from a highly dense region? That's because it's told here in the question over here that speed of light increases as soon as the light crosses this boundary. Light will only increase its speed once it enters a shallow region. So I'll be using the formula refractive index is equals to sine r divided by sine I, since this light is moving from a highly dense medium to a less dense medium. Suppose if it was vice versa, then I would have used the formula, the usual formula, n is equals to sine I by sine r. So, and I'll be using one more formula over here. Refractive index is equals to speed of light in vacuum divided by speed of light in air, as to find the angle of refraction. Now, since this is the same light, the refractive index isn't gonna change, so I'll equate both. Sine r divided by sine I is equals to speed of light in vacuum divided by speed of light in air. So the angle of refraction is what we have to find, so we'll leave sine r as it is, divided by sine 40. 40 comes from the first part, is equals to, so 1.3 v divided by speed of air, which is told to us that it is v over here. V gets cancelled, so when you multiply 1.3 with sine 40, it will be sine r is equals to 0.836. Finally, the angle of refraction will be equal to 56.7, which is also equal to 57 degrees.
Question number 8. Figure 8.1 shows a 240 volts main supply connected to an air conditioning unit and a freezer. A fuse X is placed in the circuit as shown. The freezer has an operating power of 700 watts. A. Calculate the current in the freezer. So we have the formula of current as power divided by voltage, which is equal to 700 divided by 240, and this gives the answer as 2.9 amperes of current. B. The maximum operating current of the air conditioning is 7.5 amperes. Fuses with current rating 1 ampere, 3 ampere, 5 ampere, 10 ampere, 13 ampere, and 30 amperes are available. Suggest a suitable rating for fuse X. Give 2 reasons for your answer. Alright, so the total current in the circuit should at least be the sum of current in freezer and the air conditioning unit. So if we add 2.9 with 7.5, this gives us the answer as 10.4 amperes, which means the fuse should have a higher value than 10, because if it is less than 10.4, the fuse would melt for no reason and the appliances won't work, even if the current is flowing regularly, even if it is not dangerous level. So we need to have a higher value, and I'm going to be going with 13 amperes of fuse. Reason 1 is that lower ratings fuse would melt. Alright, and selecting a value which is much higher than 13 amperes would be dangerous, and that's because suppose we have alright, so the total current is supposed to be 2.9 plus 7.5, which is 10.4 amperes. And if we have the value with if the current has a value of suppose 12 or 13 amperes running through the circuit, that would be much more than necessary, much more than required, which is dangerous for the circuit and any person operating it. So the reason 2 is We're supposed to be showing the working over here. That is 7.5 plus 2.9 is equal to 10.4. A fuse is made out of a short length of wire. Explain why fuses of a higher rating are made of thicker wire. Right, let's have a look at the working of fuse. It's a wire which melts when current above a certain value is flowing through the wire. And that's because when current flows through a wire, because of resistance, the temperature of the wire increases, and so the wire melts and gets fused. If we have a high rating of current, let's say 15 amperes, that would mean we need the wire to melt if current is above 15 amperes, right? So we need the wire to melt at higher temperatures, because if 15 amperes would mean a high current, that would in turn mean high resistance, which causes high temperature. But if this wire melted at much lower temperatures, this would not be able to work for um, high readings. So what we do to decrease the resistance of the wire is that we increase its cross-sectional area or its diameter. So as is known, resistance is inversely proportional to the cross-sectional area or the diameter. So once you increase the diameter, the resistance of the wire would decrease, and that would mean the temperature would be less. So higher values of current can pass through the wire before it gets melted. Electrical energy can be obtained from renewable and non-renewable sources of energy. One state two renewable sources of energy. There are a lot of energy sources which you can use over here. I'm going to go with hydroelectric and solar energy. Two, state one social, economic, or environmental disadvantage of one of your answers to D1. Alright, so I'm going to go with the solar source. Question number 9a. Figure 9.1 shows an electrical component. State the name of the component. Okay, this is an LDR. B. In the space below, write down the truth table for a NOR gate. Right, so we have the inputs first, and then the outputs. So NOR gate is going to be having outputs exactly opposites of the inputs. That is to say, I'll start with 0, 0, 0, 1, 1, 0, and 1, 1. In OR gate, we'd have the answers of the last three cases as 1, and this one would have an output of 0. In a NOR gate, the outputs are going to be exact opposites. That is going to be 0, 1, 0, 0, and 0. Complete the truth table shown in table 9.1 for this combination of logic gates. Alright, so we have D over here, which is the product of a NAND gate. That is, the output of a NAND gate is exactly opposite of an output of an AND gate. 0 and 1 in an AND gate would have the answer as 0. So here this is going to be 1. 1, 0 would again be having the answer as 1. 1, 1 are the only situations when an AND gate has the answer as 1. And since this is a NAND gate, the answer is going to be opposite 0 and 0. Okay, E. E is the output of an OR gate. So at least one of the inputs needs to be 1 if the answer is needed as 1. So we have 1, 1, 0, and 1. D. Referring to a simple electron model, state what distinguishes electrical conductors from electrical insulators. Alright, so conductors have mobile electrons. Question number 10. Figure 10.1 shows a simple alternating current generator. A. On figure 10.2, sketch a graph to show how the electromotive force induced varies with time for one revolution of the coil. Assume the coil starts in the horizontal position as shown in figure 10.1. Label the points on the time axis when the coil has completed quarter revolution and three-quarter revolution. Alright, so this is a position of angle 0 degrees when the coil is supposed to be horizontal. Once it becomes vertical, once it gets into this vertical position, it completes only a quarter of the cycle and forms the 90-degree angle. So when it comes into the vertical position, it no longer cuts any magnetic field lines between these two poles. That is to say, no EMF is induced when it completes the quarter of a circle, and then it turns back to this horizontal position. So that is to say half of the cycle gets completed and it forms an angle of 180 degrees just as is shown in the question. But again, that is only half of the cycle completed. So once again, when it's in this horizontal position, it cuts the most number of lines between this magnetic field, so it reaches the highest possible EMF that it can induce. And then again, that's half of the cycle is repeated, so it turns from horizontal to vertical, completing three-quarters of the cycle. And since the three-quarters of the cycle is when it is vertical, it would again it would again induce no EMF. And then the last quarter of the circle would be completed once this again for the last time becomes horizontal. Since the cycle starts with the coil in horizontal position and cutting the most number of lines, the value of EMF is going to be highest at the um, start of the cycle. So we have one entire cycle over here. This is when the coil is horizontal, and then it decreases when the coil gets vertical over here. I'm going to be marking this as the quarter cycle because it forms the 90-degree angle, becomes vertical, and cuts no magnetic field lines. Once again, this is when it completes the half of the cycle and reaches 180 degrees. So it cuts, and once again it cuts the most number of lines possible, and then it completes three-quarters of the cycle, becomes vertical position, and cuts no lines. So it has an EMF of 0 over here, and then again it gets back to its original position of being horizontal, cutting the most number of lines, and so inducing the highest EMF. B. Explain why an EMF is induced when the coil is turning. Well, while turning, a coil cuts magnetic field lines, and so it induces EMF. B. Explain why an EMF is induced only when the coil is turning. Alright, so while turning, the coil cuts magnetic field and that is the only case an EMF can be induced. C. State the name of the components labeled P and Q and state their purpose. Those are slip rings, and they provide continuous connection while the coil rotates. D. State two possible changes that cause a larger EMF to be induced. You can increase the speed of the coil rotating, and another thing can be done is increasing the magnetic field strength. Americium is a radioactive isotope. A nucleus of americium contains 95 protons and 146 neutrons. It decays by emitting an alpha particle to form a nucleus of an isotope of neptunium. Write the nuclide equation for the decay of americium to neptunium. Alright, so we have the symbol of americium as this. So the atomic number is 95 and the mass number is the number of protons plus number of neutrons. That would be 146 plus 95, which is equal to 241. Since this is an alpha decay, so we have the symbol over here as this, and alpha decay is also equal to the helium nucleus, that is to say 2 neutrons and 2 protons, which gives mass number 4 and atomic number 2, and this also forms neptunium. Alright, so we'll subtract 4 from 241, which gives the answer as 237, and 2 from 95, which is equal to 93, and this is it.
Part B. Ionization smoke detectors contain americium and two small electrodes with a small voltage between them and two small electrodes with a small voltage between them. The air between the electrodes is ionized by alpha particles so that there is a small electric current between the electrodes. Part 1. Suggest and explain the effect of smoke on the current between the electrodes in the smoke detector. So what happens normally in smoke detectors, the current would decrease because when smoke enters, its particles get ionized, disrupting constant current between the electrodes, so current decreases. The suggestion is that current gets disrupted or stopped, and the explanation to it is alpha particles get absorbed by smoke which enters. Okay. Part 2 suggests two reasons for using an alpha particle emitter in a smoke detector. So reason 1 is, firstly, alpha particles have a very strong ionization energy. And due to the first reason, reason 2 would be they travel short distance. Alright, it concludes our today's video. Thank you for watching.